everyone, my name is Kuvina and welcome back to another video. As you can probably tell from my logo, I'm a big fan of colors. My favorites are pink, purple, and magenta, but I don't think there's a single color I don't like. Another one of my passions is math and science. I've loved them my whole life, and they've been present in most of my videos. And when you have multiple passions like this, it can be extremely rewarding to find overlap between them. And so, that's exactly what I did. You might be thinking that math and colors are only tangentially related, with colors corresponding to different wavelengths of light, and that's about it. But thankfully, there's a lot more than just that. I'm talking things like linear transformations of color spaces, normalized cone cell responsivity functions, luminance and chromaticity diagrams, and of course all the math and science that goes into producing colors, both on screens and on paper. We'll get to all of those in this video, but first we need to cover the basics. So what even is color? Well, to answer that, we have to start with light. Light comes in the form of particles called photons, and due to quantum mechanics, each photon is simultaneously a particle and an electromagnetic wave. It's common to think of color as a property of these waves, but that's only partially true. The property in question is actually wavelength, which is the distance between each crest of the wave. Wavelength is detected by our eyes, which send signals to the brain that are interpreted as colors. So color isn't an inherent property of light, instead, it's a psychological phenomenon that relates to wavelength, but only indirectly. So it's not as simple as each color being a different wavelength, because there's the middle step of how our eyes convert light into signals for our brain. So what are our eyes actually doing? Within the retina, and especially the fovea, there are millions of cells called cones. They come in 3 varieties, and each type specializes in detecting certain wavelengths. Depending on the exact wavelength, each type will send a different strength signal to the brain. The intensity of the signal is determined by a mathematical function that takes one input, wavelength, and gives one output, responsivity. The first type is called the short cones. They detect light with wavelength between 400 and 550 nanometers with a peak responsivity at 440. Then there are the middle cones from 400 to 650 with a peak at around 540. Finally, there are the long cones from 430 to 700 with a peak at 570. The thing that makes these cones so useful is that their responsivity graphs overlap quite a bit. If we were to graph all 3 at once, it would look something like this. As you can see, responsivity for the short cones is a lot lower than that of the middle or long cones. But what's usually more useful is normalized responsivity. This is when we scale each graph to make them all the same height. With this normalized graph, we can now take a look at a few examples. So a wavelength of 440 will activate the short cones a lot, and the middle and long cones only a little bit. When the brain gets the signal of the short cones fully active and the other 2 types barely active, it knows to interpret this color as blue. Something like 540 will activate the middle cones fully, the long cones almost as much, and the short cones not at all, and the brain interprets this as green. And then 630 activates the long cones halfway, the middle cones a tiny bit, and the short cones not at all, and this gives us red. And with these 3 example wavelengths, you can see why the long, middle, and short cones are often called the red, green, and blue cones respectively, but I don't really like these terms. With the green color of 540, for example, the so-called red cones are activated almost as much as the green cones, and with the red color of 630, the long cones aren't even fully activated. In reality, red, green, and blue are only fractions of what the cones detect. They just happen to be where each graph peaks. Actually, that's not even true. The peak wavelength for the long cones is 570, which we see as yellow. For all these reasons, I would generally advise against calling them the red, green, and blue cones, but I do think it's fine to color code them this way because it's a very useful convention. Anyway, if we choose something like 200 nanometers, this doesn't activate any of the cones, and so the brain doesn't even know it's there. In fact, the vast majority of types of light can't be detected by us. The wavelength can be too short, as is the case with ultraviolet, X-rays, and gamma rays, and it can also be too long, like with infrared, microwaves, and radio waves. And if we scale the line to powers of 10, you can see just how small the visible part is. but of course it's still extremely important because it's the only type we can see. And if we fill in the entire visible spectrum with the colors that we see at each wavelength, it looks approximately like this. So there's definitely a lot of colors here, but there's also a lot missing. For example, where's cyan? It's usually between green and blue, but the color we get here is way too dark. And for that matter, where are all my favorites, pink, purple, and magenta? Usually color wheels loop around, and magenta is found between red and blue, but this one's just a line that goes from red to bluish purple. There's a few more like brown, gray, and beige, but most importantly, where are black and white? Clearly, the spectrum doesn't tell the full story. So then how do we find the missing colors? Well, some of them are actually pretty easy. For example, black is the color that you see in the absence of light. It's also what we see if there is light, but it's outside of the visible spectrum. And this is actually why UV is sometimes called black light. But to get other dark colors like brown, we need to consider not only wavelength, but also luminance. Luminance measures the amount of visible light photons received per area. The reason it affects color is that we have about 6 million cones per eye, so a single cone can't really do much on its own. With high luminance light, there's a sufficient amount of photons to activate every cone, so the brain sees the color fully. But with low luminance light, some cones don't get anything at all. If none of them got anything, the brain would see black, but when it gets mixed signals, it kind of mixes the two together to get a darker version of the color. Depending on the exact luminance, the color you see can lie anywhere on the gradient from the fully bright color down to black. And at this point, I want to clarify a debate about black. You may have heard some people say that black isn't actually a color because it's what you see when there's no light, but this interpretation is so problematic. Not only are there countless wavelengths like ultraviolet that produce black light, but light isn't what makes something a color. As we've seen, colors are ultimately a psychological phenomenon. Anyway, with red, green, and blue, we see the low luminance versions as variants of the original colors, like burgundy, dark green, or navy blue. But orange and yellow are so intense on their own that we consider their darker versions to be a completely new color, brown. And if you don't believe me that brown is the same as dark orange, here's a bit of an experiment you can do. Set your phone screen to nothing but orange and find a bright orange object that matches it. Then turn your brightness all the way down to its minimum value. As long as there's nothing else on the screen, you'll eventually start to see it as brown. I can't guarantee that this works for everyone, but it's at least worth giving it a try. Anyway, if we want to show all of the possible colors that can be achieved this way, a line is no longer good enough. We need 2 dimensions, one for wavelength and one for luminance. And when we fill in the entire rectangle, it looks like this. So factoring in luminance gave us a few extra colors, but we're still missing cyan, white, gray, and most importantly, pink, purple, and magenta. So if luminance doesn't help us find those, then how do we find them? Well, to do that, we need to introduce the idea of a color space. So since there are 3 types of cones, it means we have 3 variables to worry about. These are the normalized responsivity values for the long, middle, and short cones. When you have 3 variables like this, what you can do is represent them in 3D space, with each axis corresponding to a different variable. So the x-axis represents normalized responsivity for the long cones, and the y and z axes are the same thing for the middle and short cones respectively. With this, we can represent any possible combination of responsivities by a 3D vector, which basically just means a point in space. To help with depth perception, the dots are made bigger when they're closer to the camera. Since each variable ranges from 0 to 1, it means that every possibility lies within this 1 by 1 by 1 cube. So let's take, for example, a wavelength of 500 nanometers. At this wavelength, the normalized responsivity is about 0.3 for the long cones, 0.5 for the middle cones, and 0.1 for the short cones. That gives us the vector 0.3, 0.5, 0.1. So what we can do is graph this point in our color space and then color it with the color that the wavelength produces. And we can repeat this process with more and more wavelengths. So here's 480, 460, 440, 520, 540, 560, and so on and so forth. When doing this, it helps to think of normalized responsivity not as 3 separate functions, but as one single function, where the input is wavelength and the output is a point in space, whose 3 coordinates each correspond to a different cone type. This way, we get what's known as a parametric equation, where you can basically trace out the path of a point in space as you change the input variable. So now we just have to do this in 3 dimensions with the normalized responsivity functions. But wait a minute, what even are the equations for responsivity values? We know what they look like, but how are they defined mathematically? Well, the thing is, they're not mathematically defined. They're based on scientific data that can't be represented with a simple equation. What we can do, though, is approximate them. I've chosen to use the normal curve. It's defined by y equals e to the negative 1/2 x squared, with a few parameters that can change the shape. The normal curve is found all the time in nature, so it's often a very good approximation for things. And if we get the parameters right, we can produce the following graphs, which as you can see are very good approximations. Now that we have the equations, we just have to graph it and we get a curve like this. It starts at the origin with ultraviolet, then moves up the z-axis with blue light. As it moves down again, it begins to move up the y-axis with green light, and soon it also moves up the x-axis with yellow, orange, and red light before returning to the origin with infrared. Now this might seem kind of pointless because it doesn't give us any new colors, it just shows us what we already have, but maybe you'll remember that the space of potential cone response combinations was this entire cube, and this one-dimensional curve only shows us a portion of it. So to find the missing colors, we need to look at other locations within the cube. The first place that might stick out to you is the top left corner. You can see that the red section connects to the green section, which itself connects to the blue section, but red and blue don't connect to each other. Instead, they both just approach 0. But if we had a way to activate both the long and short cones, then it would make new colors in this gap. And as it turns out, this is exactly where we can find magenta. Purple is also found nearby, but a bit closer to blue. And then there's this area on the right here. Since peak responsivity is so close for the long and middle cones, it allows wavelengths where both types are activated almost fully. But for middle and short, they're not close at all, so we don't get as far from the origin in this section. But if we could activate both of them some more, we would get a color further out and closer to the camera, and this is where cyan is found. And then finally, what if the 3 types of cones were activated all at once to their maximum extent? Well, this is actually how we make white, and a lot of other colors are found in between these points of interest. So pink is between magenta and white, beige is in between yellow and white, turquoise is in between cyan and green, and the list goes on. And remember, you can always lower the luminance to get a darker color. In this color space, that actually has the effect of moving all points towards the origin, which is where black is found. This is how we got brown from earlier, and it's also how we find our last major color, gray, in between black and white. Any color you can think of will be somewhere within this color space. But there's still an issue. We've already looked at each visible wavelength, and all that gave us was the parametric curve. So it raises the question, what kind of light actually produces these colors? Well, so far, we've only been looking at monochromatic light, which is when every photon in a beam of light has the same wavelength. This produces what are known as the spectral colors, which are found along the curve that we graphed. In real life, though, light usually consists of many different wavelengths all at once. So let's take, for example, light with a mix of 450 and 630 nanometers in equal proportions. When the light reaches the cones, half of them get the 450 and half get the 630, which produces mixed signals. But what the brain cares about is the average across each type. When we find the corresponding location in the color space, it's in between purple and magenta, and so that's exactly what the brain sees. But instead of doing that whole process, there's an easier way to find that location. You just find the 2 component wavelengths and take the weighted average. So if there was more blue light than red, the point would be closer to blue, and vice versa. But when there's an equal amount of both, the point is halfway between them. There's an infinite amount of potential combinations, and the way we visualize them is with an emission spectrum, which can be graphed as a spectral power distribution. It's just a function that gives us the amount of light present for each wavelength. So for example, the emission spectrum of pink light will look something like this. You can see it as a lot of long and short wavelengths, but not as many of those medium ones. In the color space, we take the weighted average of these and the point we end up with is right where pink is, so that's how we see it. And this is how the rest of the colors are formed, not from individual wavelengths, but from combinations of spectral colors. If we fill in the entire volume of color space that can be reached with combinations of spectral colors, it forms this kind of cone shape. This is called the visible gamut, and any color you can think of will be somewhere within it. It's also what's known as a convex set, which means you can never get a color outside the set by combining ones within it. But that presents an issue. Earlier, I said that the space of all potential colors was this 1 by 1 by 1 cube, but the visible gamut is still only a fraction of it. So what kind of colors do we find outside the visible gamut, but still within the cube? Well, these are known as impossible colors, because there's no combination of spectral colors that can reach them. One example is hypergreen. This is what you would hypothetically see if the middle cones were fully activated, but none of the other cones were activated. This is impossible because any wavelength that activates the middle cones will also activate one of the other types. So this three-dimensional color space is cool, but it's hard to visualize. Wouldn't it be nice if we had a way to visualize all the colors in 2 dimensions? The answer is yes, of course it would be, but it's impossible to do so. Luckily though, there's a trick. So if you remember from earlier, lowering the luminance of a color has the effect of moving it towards the origin. But the cool thing about it is that even when you change luminance, there's some intrinsic quality of the color that doesn't change. This is called chromaticity, and straight lines from the origin can be thought of as lines of constant chromaticity. Even though you need 3 dimensions to show all possible colors, you only need 2 dimensions to pass through all possible chromaticities, so our goal is to form a 2-dimensional chromaticity diagram. There are so many different approaches you could take, but the most popular one is called the CIE 1931 XY chromaticity diagram. But to understand how it's formulated, we first need to look at the CIE color space. A color space is just a way to arrange colors in 3D space, so there's an infinite number of ways to do this. The one I've been using is called the LMS color space, which is based on cone response. But the most influential color space is the CIE 1931 XYZ color space. It's unique because it actually takes into account the psychology of color perception. So remember when I showed responsivity from each cone type? The long and middle cones had a lot more responsivity than the short ones, and what we did was normalize all 3 types, but this discrepancy actually has a significant effect on how we see colors. If we add all 3 functions together, then this gives us a function of total responsivity. As you can see, total responsivity for green and yellow wavelengths is very high, while reds and oranges are a bit lower, and then blue is a lot lower. That helps explain why we see colors around yellow as a lot brighter than others. This is called relative luminance, but it's a confusing name because it's unrelated to actual luminance. Anyway, the CIE color space basically takes the LMS space and transforms it so that the y-axis roughly corresponds to relative luminance. The way it does this is with a linear transformation. To determine where a point will end up in the new color space, you take its coordinates in the old color space, multiply them by constants, and add them together. These constants are usually arranged in a matrix so you can do vector matrix multiplication. A special property of linear transformations is that straight lines remain straight even after the transformation. Another property is that the origin never moves. Due to these facts, our lines of constant chromaticity are still lines of constant chromaticity even in the new color space, which makes it just as practical as the LMS space. But the big advantage of the CIE color space is that it makes the curve of spectral colors into a much more manageable shape. So the CIE color space is basically what everything is based on, and that includes the chromaticity diagram. Now how do we actually construct the diagram? Well, we just need an algorithm that takes colors from the 3-dimensional color space and maps them to the 2-dimensional chromaticity diagram in such a way that any 2 colors with the same chromaticity will end up in the same location. The CIE diagram achieves this with the following method. First, you take the color and figure out what chromaticity line it's on. Then you follow that line until it intersects the plane x plus y plus z equals 1. Then take the x and y coordinates of the point where it intersects. Finally, take the original color and plot it in the chromaticity diagram at those same x and y coordinates. If we perform this process for all of the spectral colors, we get the following, which is basically the outline of the full diagram. My graph is a slightly different shape, but I'm guessing that's just because of my approximations for the responsivity functions. Anyway, to get the full diagram, we just need to do the same process with one color of each chromaticity. But each chromaticity has infinitely many colors, and we can only choose one, so what we usually do is just use the one with the highest luminance, and this finally gives us the full diagram. The curved outline represents the spectral colors at varying wavelengths, while the straight section is called the line of purples. Since we use maximum luminance for each chromaticity, some of these are actually brighter than the correct spectral colors, but it doesn't matter that much because they still have the same chromaticity. The cool thing is that this diagram makes it really easy to combine colors, so with a mix of 450 and 630 nanometers, you can see that the midpoint is right near magenta like we saw before. To get white, you could combine every spectral color at once, or just two from opposite sides, like yellow and blue. So at this point, we know how to combine spectral colors to form other colors, but how are these combinations created in real life? Well, there's so much that could be said about the physics behind light, but for now, I'll make it short. So most objects we see don't actually produce their own light. Instead, they absorb photons from the environment and then re-emit them in all different directions. This is called diffuse reflection. On the atomic scale, individual electrons absorb the incoming photons and use this new energy to move to a higher electron shell. They can also release photons to move to a lower shell. Every shell has its own specific energy level, meaning every combination has a specific energy difference. For an electron to make the transition, the photon that it absorbs or emits needs to have an energy equal to the energy difference between the shells, so photons can only be reflected if their energy is on the list, otherwise they won't get reflected. Photon energy is actually proportional to frequency of the wave, which itself is inversely proportional to wavelength. That means that only a few wavelengths from the visible spectrum end up getting reflected. The energy levels of electron shells are different for every element, which gives each one its own signature set of spectral lines. With hydrogen, for example, we get these four lines in the visible spectrum, called the Balmer lines, corresponding to electron movement to shell 2. If we find these wavelengths on the chromaticity diagram and take the weighted average, we get pink, which is exactly why we see a hydrogen discharge tube as pink. But you might notice that the lines have non-zero thickness to them. That's because the photon's energy doesn't have to be exact. In fact, based on a variety of factors including density, the lines can broaden beyond the point of recognition, at which point it makes more sense to use the spectral power distribution. So a low-density vapor-filled tube will have a few sharp points, but something solid will have a more continuous emission spectrum. So this is why materials have different colors based on their chemical composition, and if we want to make something a specific color, we just need to add a pigment, which is just some material whose emission spectrum is of particular significance to us. So that was reflection, but what about light sources? Well, there are two main types of light sources, incandescent ones and luminescent ones. Incandescence is when an object produces light based on its high temperature. This can be through things like combustion, aka fire, or blackbody radiation, where the emission spectrum of a hot object is approximately wave-shaped and the peak wavelength is inversely proportional to temperature. For something cold like a human, the peak is way in the infrared, so we don't produce visible light. But for really hot things like stars, the peak can be in or near the visible range, so they produce visible light. This is what we get for a 3000 Kelvin star. If we look at just the visible part, there's a lot of reds and not so many blues. This results in orange, which you can see on the chromaticity diagram. A 6000 Kelvin star has about even amounts of every visible wavelength, making it basically white. And a 10,000 Kelvin star has a lot of blues and not so many reds, so its final color is light blue. If we look at all the colors that can be produced by blackbody emitters, we get a line called the Planckian locus. It starts off at red, then goes to orange, yellow, white, and finally light blue. All this talk about stars might have you wondering about the most famous star of all, the Sun. It's the perfect temperature to produce all wavelengths of visible light in approximately equal proportions, making sunlight almost perfectly white. This was famously demonstrated by Isaac Newton using a prism to refract sunlight. The angle of refraction varies slightly based on wavelength, which separates white light into individual wavelengths. And this is the same property that forms rainbows, where the raindrops function as tiny prisms. Ideally, we would get the spectral colors, but the beam of light can never be perfectly uniform, so the spectrum we actually get looks a bit different. When Newton saw this, he divided it into 5 main colors, which he called red, yellow, green, blue, and violet. Later on, he added orange and indigo because he really liked the number 7. This has the catchy acronym ROY-G-BIV, and to be honest, I kind of hate ROY-G-BIV. You see, it only really works with outdated color terms. What Newton called blue, we would call cyan. What he called indigo, we would call blue. And what he called violet, we would call dark blue. Unfortunately, people still use the acronym with modern color terms, which leads to cyan getting left behind. Also, it's worth noting that neither of these contain purple. Even though rainbows can contain purple, that's due to something called supernumerary bands, where a smaller and fainter rainbow forms, and the red of the small one mixes with the blue of the big one, forming purple. Anyway, let's get back to sunlight. Even though sunlight is white, the sky isn't white. Instead, it's azure, which is in between blue and cyan. So why does the sky look like this? Well, when you look at the sky, you're not actually seeing direct sunlight. Instead, you're seeing light that's been reflected by particles in the atmosphere. Since the particles are so small, it leads to a phenomenon called Rayleigh scattering, where shorter wavelengths are reflected more often than longer ones. Because of this, the emission spectrum of the sky ends up looking like this, which ultimately results in azure. Meanwhile, the sun itself looks slightly yellow because you're seeing the light that hasn't been reflected. So the sun is a natural light source, but in the past century, artificial light sources have really taken off. This can be through incandescence, which is how lanterns and the first light bulbs worked, but modern technology has allowed us to make use of the other type of light source, luminescence. The first important type is electric discharge, where a vapor-filled tube receives an electric current which ionizes the atoms, causing them to emit light. Compact fluorescent lights, or CFLs, achieve this with mercury vapor, which produces ultraviolet light. They then combine this with another type of light source, fluorescence, where a material called a phosphor receives high-energy light like ultraviolet and then re-emits it as something lower energy, like visible light. Fluorescent light bulbs are a lot more energy efficient than incandescent ones, but even more energy efficient would be LEDs. Diodes only let electric current flow in one way, and they achieve this by combining 2 different types of semiconductors. Electrons jump from one side with excess electrons to another side with missing electrons. This new side is more energetically favorable, and so the electrons release this energy in the form of photons, with energy equal to the amount lost, giving them very specific wavelengths. The current gives a constant supply of new electrons, which results in the light-emitting diode emitting light. So let's compare the emission spectra of the 3 different light sources. You can see that incandescent lights produce a very smooth emission spectrum, so they pretty much only come in yellow. The emission spectrum of CFLs indicates where you would find spectral lines, and then LEDs are able to specialize in specific wavelengths. Now we can take a look at how computer screens work. We've seen how every color is just some combination of spectral colors, so it makes sense that computers would make many different colors by combining just a few, which are known as primary colors. The area of colors we can achieve with a system is called its gamut, and we want to maximize the gamut while using as few primary colors as possible. To get a non-zero area, we need at least 3 primary colors, and just looking at the chromaticity diagram, it's pretty clear what we should pick. Since the 3 primary colors are red, green, and blue, technology that uses them is called RGB technology. Unfortunately though, we can't exactly produce these pure spectral colors. The first type of RGB technology was CRT, or cathode ray tube, and its gamut looks like this. It makes use of phosphorescence, which is similar to fluorescence in that they both use phosphors. The blue and green phosphors were pretty easy to find. The green kind uses zinc sulfide activated with copper, and the blue kind uses zinc sulfide activated with silver. The red kind, though, was actually really hard to find, and this significantly delayed the development of color TV, but eventually one was found. yttrium oxide sulfide activated with europium. The emission spectra of the three phosphors generate the primary colors that we saw earlier. So each pixel has all three types of phosphors, and to set that pixel to the correct color, each phosphor is set to a specific luminance, and these combine to form the color. These pixels are so small that we can't even distinguish the red, green, and blue sections, and instead just see the pixel as a single color. Modern screens don't use CRT though. They use LCD or liquid crystal display, which can have a better gamut. But if this is the gamut of the screen you're watching this on, how does it possibly produce the full chromaticity diagram? Well, it kind of cheats a bit and just shows the colors that are as close as possible. For that reason, these images are only approximations. The way LCD works is very complicated, involving polarizing the light, which basically changes the angle at which the waves are oriented. But it still works by the same basic concept of combining three primary colors. What about printers though? They can't just combine light sources because the result should be a piece of paper, which isn't a light source, it's just a reflector. So instead of additive color mixing, where you start with black and then add the primary colors in the form of light sources, printers use subtractive color mixing. This is where they start with white, which reflects all colors, and then they subtract the primary colors from it to get the desired color. But they're not physically removing anything from the paper. In fact, they're adding something. So what is it that they're adding? Well, instead of subtracting red, green, and blue, they add anti-red, anti-green, and anti-blue. But what does that mean? Well, a green object will only reflect green wavelengths, but an anti-green object will reflect everything but green. The resulting color is magenta, but that's kind of irrelevant. All we really care about is the anti-color property. If we take the anticolors of red, green, and blue, we get cyan, magenta, and yellow. So printers can make any color by starting with white paper and then adding the three pigments. Most printers also use a fourth pigment, black, which helps make things darker. The black pigment is called the key, and so this printing technology is known as CMYK. The way images are generated with printers is very similar to how it was with screens, but instead of activating each light source at a different luminance, they distribute particles with different sizes to create the image. So we've seen how computers make colors by combining three different primary color light sources at different luminance levels. This gives us three variables, so just like with cone response, we can assign each one to an axis of 3D space. Each one has a max value, which we'll call 1, so again, it gives us a cube of potential colors we can make by combining these. Unlike with cone response though, each variable can be controlled independently, which means we can actually reach every location within the cube. And if we fill in the cube with the colors that we get for each combination, we get the one and only RGB cube. But it's important to note the differences between this and the LMS space. For example, a pure green here is found at 0, 1, 0, but that same point in the LMS space was the impossible color hypergreen. And even though the RGB cube is a full cube, it still has fewer colors than the visible gamut in the LMS space. And this can be easily seen in the chromaticity diagram. Anyway, the RGB cube is how computers generate colors. They assign a value to red, green, and blue content for each pixel. These take integer values from 0 to 255. But why 255? Well, it has to do with binary, which is how computers store data. In base 10, we have 10 digits 0 through 9, but in binary, there are only 2, 0 and 1. Binary digits are called bits, and when you have 8 of them, it's called a byte. The number of combinations for 8 bits is 2 to the 8, or 256, and each combination corresponds to a number from 0 to 255. So by limiting red, green, and blue to 8-bit integers, computers only need 3 bytes to represent a color. But when we talk about computer colors, we usually use hex codes. They use hexadecimal, which is base 16. It has the digits 0 to 9 from base 10, and then for the remaining 6 digits, it uses letters A to F. Counting in hexadecimal is just like counting in base 10, but each digit can go up to F before you have to change the next one. With 2 hexadecimal digits, you have 16 squared or 256 combinations, which is the perfect amount for 1 byte of information. So to form a hex code, you take red, green, and blue content of the color and then convert them to hexadecimal and put them together to form a 6-character string. And if you want to convert a hex code back into the red, green, and blue components, here's how. So first, you separate it into 3 2-digit sections. Then for each one, convert any letters into their corresponding numbers. Then you multiply the left one by 16 and add it to the right one, and this gives you the 3 numbers. So this RGB system is cool, but it's not the most intuitive. Depending on the red and green values, the blue axis can go from black to blue, orange to pink, brown to purple, and a lot more. It would be more intuitive if each axis always controlled the same thing, like how bright the color is. And this is exactly what the HSV color space attempts to do. Its 3 variables are called hue, saturation, and value. Saturation and value range from 0 to 100, while hue ranges from 0 to 360. So if you remember from earlier, changing a color's luminance doesn't affect its chromaticity, so it makes sense for one of the variables to control luminance, and that's approximately what value does. That leaves us with the other 2 variables to describe chromaticity, and at this point you might notice something. All of the colors seem to get lighter towards the middle, eventually becoming white in the very center, and so it makes sense that one of the variables should represent distance from the middle. That's saturation, and it leaves hue to measure angle around the center. The chromaticity diagram is based on the CIE color space, which itself is based on the LMS one. Since this is on the computer though, it should be based on the RGB cube, so we need an algorithm to convert RGB values into HSV values. The way to do that is as follows. So first of all, we're going to divide RG and B by 255, so that they range from 0 to 1. I'm calling these lowercase rg and b. Then we're going to find the minimum and maximum out of the 3. These will be m1 and m2 respectively. Then finally, delta is the difference between those. Now we have all the intermediary variables, so we'll start with value. It's the easiest because it just equals m2 times 100. This means that surfaces of constant value correspond to 3 faces of a cube, where lower value means a smaller cube. Next is saturation. It's defined by S equals delta over m1 times 100. This means that lines of constant value and saturation correspond to triple L's along the cube, where lower saturation means they're closer to the triple point. Also, if you get 0 over 0, it just means that saturation has no effect on the color, so we just pick 0. Lastly, there's hue. It basically represents distance along this triple L, where we start on the red face and move anti-clockwise. The length of any 1/2 L is equal to delta, so if we divide the distance by delta, it will range from 0 to 6. We'll call this value x. Then if we multiply by 60, it will range from 0 to 360 like we want. But the way you calculate this distance differs depending on which face you're on. If red is the maximum, it means you're on this left face, so distance is g minus b. If g equals b, you get x equals 0. On the right endpoint, g minus b equals delta, so x equals 1. And on the other endpoint, g minus b equals negative delta, so x equals negative 1. This means x ranges from negative 1 to 1, but we don't want negatives, so we use the modulo operator by 6 to make it go from 0 to 1 and then 5 to 6. Finally, we multiply by 60 to get this 1/3 of the hue formula. Now if green is the maximum, it means you're on the right face, so the distance is b minus r. It's basically the same concept, but this time we add 2 to make it from 1 to 3. This accounts for the starting point still being on the red face. This gives us the next third of the hue formula. Finally, if blue is the maximum, you're on the top face, so we use r minus g. The same thing applies, but we add 4 this time, and this gives us the full hue formula. Again, if you get 0 over 0, it just means that hue doesn't affect the color, so we just use 0. And with that, we finally have the HSV color space. If we arrange it like before, with each axis being a different variable, then it forms this square prism shape, which is certainly interesting, but there's a better way. Cylindrical coordinates use 2 distances and 1 angle to represent points in space. If we set the angle theta equal to hue, and the distances r and z equal to saturation and value respectively, then we get this beautiful cylinder. But you might notice something. The top face has many different colors, while the bottom face is all black. So it makes sense that it should end at a single point. and we can achieve this by setting R equal to saturation times value. This gives us the HSV cone, which is my favorite way to arrange colors. And if you've ever seen a color picking tool like this, it basically takes a cross-section of the cone at the desired hue. Now that we have a great way to pick colors, let's make a color scheme. So the RGB cube is a great place to start because we can take a 3x3x3 grid of points and it gives us 27 colors. This is the basis for my color scheme, although I do modify them a bit. But instead of viewing them in the RGB cube, we can take a look at where these points end up on the HSV cone, and it makes this really nice pattern which helps us organize them better. And now we can start naming them. So first of all, in the center of each layer we have black, white, and gray. Then in the top layer we have what I call the main 6. These are red, yellow, green, cyan, blue, and magenta. These, along with black and white, make up the 8 corners of the RGB cube. Then the next set of 6 is what I call the in-between colors, because they're in-between pairs of the main 6. These are orange, chartreuse, turquoise, azure, purple, and cerise. My logo includes the main 6 along with orange and purple to form what I like to call the 8-hue interpretation, because I think these 8 are the most distinct. The remaining colors can be divided into 2 groups of 6, lighter versions of the main 6 and darker versions of the main 6. On screen are the names I've chosen for them, but these names are not yet finalized. My full color scheme includes these 27, as well as 9 more, which I think are distinct enough to be separate. If you're interested in the hex codes, then here they are. But keep in mind, my color scheme is still a work in progress. And now we finally reached the end of the video. If you have any questions, feel free to ask in the comments, and I'll do my best to answer. This is by far the longest video I've ever made, and it took a lot of work, so if you want to make it all worth it, I would very much appreciate if you would like the video and subscribe to the channel. I have a lot of other videos you can watch, and I have more coming soon, including Relativity Part 4, which you won't want to miss out on. Thank you for watching, and I hope to see you soon.